Welcome to the third part of the problem solving session for Chapter 5. Question 10 states the following. An Atwood machine is an arrangement of two unequal masses hung vertically from a rope over a pulley. If M1 is given to us as 2 kilograms and M2 is 5 kilograms, determine the acceleration of the masses and the tension on the single rope that passes by the pulley. Here, the first thing we want to do is to draw a free body diagram for each of the masses, which has been done for us here. We'll go ahead and reproduce it, and specifically we make note of the fact that we have two unknown quantities to solve for, both of which happen to be the same value for mass 1 and mass 2. That is, each of the masses has the same acceleration and the tension on either side of the rope has the same value. Therefore, the two unknowns that we're solving for are A, the acceleration of each of the masses, and T, the tension in the rope. So we will need two equations to do this, and we will obtain these equations from each of the masses. So let's begin with mass 1. Mass 1 has a weight m1g downward and the tension that the rope exerts upward. We are also told that mass 1 accelerates upward. Newton's second law, in the y, there are no forces in the x. The net force on, let's call this M1. The net force on M1 is equal to M1A. Notice the acceleration is positive since the mass is accelerating upward. Okay, so the forces are T minus M1G equals M1A. Let's go ahead and solve in terms of one of the unknown quantities, T. And so this gives us our first equation of unknowns, T equals M1G plus M1A. Okay, now let's write an equation for the second mass, M2. In this case, the force of gravity is also acting downward. The force of tension is acting upward, but this mass is accelerating downward. And so here we have to be careful to note that in this case here, the net force on M2 will be minus M2A because the acceleration is downward, and we have to specify that since we took the acceleration initially to be, for the first mass, that is, to be upward, which is in the opposite direction as the existing acceleration. So here once again, we solve for T as M2G minus M2A. This gives us a second equation that contains the same two unknowns, and now it's very simple. We just set both sides equal to one another, and so we have M1G plus M1A equals M2G minus M2A. Collect all the A terms on one side, A times M1 plus M2 equal to G times M2 minus M1. Solve for A. This gives us a value of 4.2 meters per second squared. Use one of the equations for t. Let's say t equals m1 g plus m1a, and that gives us a value of 28 newtons. So, two equations, two unknowns, use substitution to eliminate one of the unknowns and solve for the other. Question 11. Determine the coefficient of static friction, μs, for a block that is placed on a rough inclined surface by measuring the angle theta, which by the way that Q is a theta, when it just begins to slip. Now here's something we have to keep in mind. The acceleration along the y direction of this block will be equal to 0 since it will maintain contact with the block, with the incline rather. But also just beginning to slip implies that we are still working at the instant before motion occurs. In other words, Fs here is at the maximum value of mu s times n. So there will be no acceleration for our block along the x or the y direction. Let's draw a free body diagram. Here's x, here's y, here is our block, here is, friction along the parallel to the incline. Here is the normal force. I really can't get these lines straight. And here is the force of gravity, mg, which is going to have components along the inclined coordinate system, where the vertical component is mg cosine of theta. Here is theta right here. And we've got the component of mg that is parallel to the incline, mg sine theta. We no longer need to make use of mg because now we have the components. Okay. Newton's second law. The forces along the x direction have to equal to 0, and these are mg sine theta, which is along the positive direction, minus the force of static friction. And we can rewrite this as mg sine of theta. The force of static friction will be given by mu s times the normal force, which we have yet to determine from our equation for Newton's second law in the y direction, which we are about to obtain now. Here you can see that n minus mg cosine of theta is equal to 0, which implies n equals mg cosine of theta. And so now we can take this value of n, plug it into here, and this gives us mg sine of theta minus mu s mg cosine of theta equals 0. You can see that the mg's are going to cancel. So we have mu s cosine of theta equals sine of theta, or mu s equals the tangent of theta. And in fact, Given the angle theta of the incline, we can determine the maximum coefficient of static friction just before the block will begin to slip. Okay, question 12. The following systems are in static equilibrium. What do the spring scales read in each case? Now here it's important to notice that the spring scale only reads what is being pulled on one side of it. That is where the spring is being pulled, either in this case to the left, or in this case downward, or in this case here at an angle that matches that of the incline. So we don't care what is happening on the other end of the spring scale, where it's being supported. All we care about is what is the force that is pulling on the end of the spring scale that registers a value. So here we begin, and we see that the pulling here is the tension of the rope, which is a direct result of the weight of this mass, 5 kilograms times 9.8 meters per second squared, is 49 newtons. So in the first case, the spring scale reads 49 newtons. In the next case, you can see that we have the pull that is occurring due to both blocks, each of which has a weight of 49 newtons, giving us a total force of 98 newtons. And in fact, this is what the spring scale reads in the second case. In the third case, we have to consider the components of gravity. So we have the component mg, which is perpendicular to the incline. We have the component of mg, which is parallel to the incline, and of course mg itself, which is perpendicular to the ground. So we have mg sine theta here, mg cosine theta here. We don't care about this mg. This is a 30-degree angle, and you can see that the component which is pulling on the spring scale is in fact only the horizontal component, or the component which is parallel to the incline. Mg sine theta is 49 newtons times the sine of 30 degrees, and that gives us 24.5 newtons, which is what the scale registers. Next problem. Here we have a situation that is somewhat similar to the Atwood machine, in that we have two blocks that are connected by a string that passes over a frictionless pulley. However, one of these blocks is lies on the surface of a rough table, horizontal table, and so there's friction, and we're told the coefficient of kinetic friction in this case, so we have to take that into account. And once again, we're finding the accelerations of the acceleration of the masses, because there will be a common acceleration. Each of the masses experiences the same value of acceleration. And we're also asked to determine the tension on the string, which again will have the same value on either side. So we need two equations to satisfy the two unknowns. Let's begin by drawing the one of the masses, the hanging mass M2. We've got the force of gravity downward, M2G. We've got tension upward, T, and we know that the mass is sliding downward. So A is downward, and we must take it as negative. So here, when we set all of the forces along the vertical, we have to set them equal to minus m2a to take into account the downward acceleration. And these forces are T minus m2g equals minus m2a, or T equals m2g minus m2a. And so here is one equation containing one of the unknowns. All right, let's look at the other block. Let's look at M1. In the case of M1, we've got both forces along the horizontal. Here that would be T as well as F sub K, the force of kinetic friction, and forces along the vertical, M1G, and normal force. However, since the mass M1 stays in contact with the surface, we know that the forces along the Y equals 0. And so N minus M1G equals 0. N equals M1G. And so it's almost an unnecessary piece of information for us because it does not contain an unknown. However, along the x direction, we have the net force equals M1A, or Fk negative plus T equals M1A. T equals Fk plus M1A, where Fk is equal to mu k times N. N is M1G. So in fact, it was useful for us to obtain N plus M1A. Here we go. Now we have our second equation in T. We set both sides, both T's, equal to one another, and that gives us M2G minus M2A equals M1A plus mu k M1G. Set all the A's on one side, M1 plus M2. Set all the G's on the other side, G times M2 minus mu k M1. Solve for A, and we obtain A equals 5.6 meters per second squared. So we now have the acceleration of these masses, and now to get T, we use one of the two equations in T, say for example M2G minus M2A, and that gives us a value of 37.8 newtons. Okay. Next problem, and in fact last problem, we have two objects, M1 and M2, connected by a light string passing over a frictionless pulley. The incline is frictionless as well and makes an angle of 55 degrees. Determine the acceleration of the two masses and the tension in the string. So here the complication arises from the angle of the incline, but this problem is very similar to the one we solved, except we're going to have to deal with an angle theta. The first part is quite straightforward, as we've done for M1, for example. In the case of M1, we've got M1G, we've got T, and we've got an upward acceleration. So Newton's second law, the net force in y equals m1a, or T minus m1g equals m1a, T equals m1g plus m1a. Okay, well that was easy enough. Now let's work on the harder one. Here we need to draw our incline, put our mass right here. Here is our y direction. This is our x direction. Here is gravity, m2g. Here is the component of gravity that's perpendicular to the incline, m2g cosine of theta. Okay, here's theta. And here's the component of gravity, which is parallel to the incline, m2g sine of theta. Of course, we have a normal force and here, and if we had friction, we would add that along here. All right, let's see. Well, in this case as well, we know that for, let's label this as M1, this is M2. In this case for M2, N minus M2G cosine theta is equal to 0 since the block stays in contact with the incline, and so we solve for N as M2G cosine of theta. Okay, now we don't need to make use of that. Let's see, how about the net force in X equals M2A, where A is going to be along the positive X direction. And so here, notice that in this situation here, A is positive in both the case of M1 and M2. Here we have M2G sine of theta is equal to M2, we forgot something very important, and that is that we have tension, oh boy, pulling back this way. And so minus T plus M2G sine theta equals M2A. Okay, T then is equal to M2G sine theta minus M2A. Once again, we set the T's equal to each other, and this gives us M1G plus M1A equals M2G sine theta minus M2A, collecting the A's on one side, A times M1 plus M2 equals G times M2 sine theta minus M1, and this gives us a value of A equals 3.58 meters per second squared. And once again, using one of the T's, we obtain T equals 26.8 newtons. Well, this concludes the third and last part of the problem solving session for Chapter 5. See you next time.